Yeah, welcome back. Uh, we have seen the definition of positive definite matrix in the last class. Then we have seen the applications of positive definite matrix. So we have appreciated that. So now I think we are in a position to look into more, we have the motivation, I would say, to dive deeper into the properties of symmetric positive definite matrices and develop Cholesky decomposition, which is a very computationally efficient way of checking positive definiteness uh, of a matrix, symmetric matrix A, whether it is positive definite or not. So towards that end, let me start with first. I will just focus on developing the Cholesky decomposition, because there are many other characterizations of positive definite matrices, but those are really not very useful computationally, though you see them in textbooks a lot. But if you really want to check whether a matrix is positive definite or not, you should actually see whether you can complete the Cholesky decomposition of the matrix, which is basically asking that can I write the matrix A as R transpose R, where R is a upper triangular matrix, just like what we had got in QR decomposition. In fact, the R term comes from there. If you can proceed to complete this form of decomposition, then it means that your matrix A is positive definite. That follows from the fact that if A can be written as R transpose R, then X transpose AX will become equal to sec square of the norm of R times of X, which is always greater than or equal to 0. So guarantees that it is a positive semi-definite matrix. And if R is non-singular, that is all its diagonal values are greater than are not equal to 0, then Rx will always be a vector y will always be not equal to 0 if x is not equal to 0. So therefore, the square of the length of Rx will always be greater than 0 if x is not equal to 0. So Cholesky decomposition can be done in order n cube. Calculation of Cholesky decomposition is only order n cube, and therefore is considered a very efficient way of checking positive definiteness. More about it later. First, let's arrive at that place. So to that end, I start with the first characterization, that if A is a symmetric positive definite matrix and lambda V be its eigenvalue eigenvector pair, some eigenvalue eigenvector pair, then first of all this eigenvalue will be greater than 0. That means every eigenvalue of a positive definite matrix is greater than 0. That's what I am trying to say. So to prove that, there are two things. If I say something is greater than 0, then first of all I should show that it has to be real, and then I should make exclude the the 0 and the negative values and say that show that it is greater than 0. So first of all, to show that the eigenvalue is real, I only require symmetricity of A. For that, I don't actually need the the positive definite part of it. I am saying that if A is a symmetric positive definite matrix. So right now, to show that the eigenvalue is real, only thing that I am going to use is that A is a symmetric matrix. So if let's say that to the contrary, that it can have a complex eigenvalue of the form A plus JB, then I'm going to show that B has to be equal to 0. So suppose this is a complex eigenvalue, and unless otherwise stated, my V eigenvector is always normalized to unit length. That even if I forget to say this, please understand this. So AV eigenvalue eigenvector equation says that A times of V will be equal to lambda times of V. Now, at this point of time, since I am assuming A can be complex, I have to also assume that V is also a eigenvector of complex values inside it. So therefore, when I multiply it by V star, which is V transpose and then complex conjugate, then I will get this as V star AV is equal to A plus JB V star V, and V star V becomes a a real a number which is strictly greater than 0, because it's the length of it's 1. In fact, I said I am taking a unit length vector, so it's 1. So therefore V star AV becomes equal to A plus JB. This is nothing but equal to A plus JB, and when I take its complex conjugate, this whole thing's complex conjugate, then the V star will come here. This V star will become and go as V here, and here will come A star. But because my matrix is real and symmetric, if A is a real and symmetric matrix, as we are dealing in this course, then A star will be equal to A. So taking a complete conjugate of this again gives me the same thing, and this is unity, this also remains one only, and so this will therefore, but this will change, this will become its own, this will be, I'm sorry, so but we will have to take the complex conjugate of this eigenvalue, which will come here as A minus A JB, and so therefore what we are getting is that V star is the same thing, is also equal to A minus JB, which if we equate therefore A plus JB equal to A minus JB, then we get B equal to 0. And so eigenvalue, first part we have proved that the eigenvalue is real. Now, this automatically means that the eigenvector is also real. There is a real eigenvector corresponding to the real eigenvalue. So for that, to the contrary, you assume that it has to be necessarily complex. Then you can write it as the eigenvector can be written as a complex combination of the real part and the imaginary part. And then I use the basic definition AV equal to lambda V, substitute VRE plus IVM equal to lambda times of VRE plus IEM. Now, since lambda is real, VRE is real, AVRE is real, so equating the real part, I get AVRE equal to lambda times of VRE, and equating the imaginary parts, I get AVM equal to lambda times of AVM. Hence, basically what we are saying is these are actually the real part and the imaginary part, these two subvectors are indeed actually the eigenvectors, which proves that actually really there is nothing like a complex eigenvector standalone. Essentially, standalone, the eigenvectors corresponding to this real eigenvalue are also made up of is also a real vector. That is, it is coming from Rn and not from Cn. I mean, of course, Rn can be considered as a subset of Cn. That way is a different thing, but it is essentially Rn, does not require any complex vector to be represented. So we have reached this nice feature that hence it is essentially a real eigenvalue implies real eigenvector. Once we are done with that, then we can dispense with taking V star. We can dispense with taking V star and instead take V transpose. So if I take therefore now, because why do I take V transpose? Because when I want to check positive definite or use positive definiteness property, I have to use the fact that V transpose AV is greater than 0. So I multiply this from left hand side by V transpose. So this will become equal to lambda V transpose V, which is same as the lambda times square of the length of the V vector, which is unity, and therefore I come to the conclusion that this is equal to lambda, but because my A is positive definiteness, so this has to be greater than 0, therefore I come to the conclusion that lambda is greater than 0. So if A is SPD, the eigenvalues have to be always greater than 0. Now, once I have reached this part, then I am going to come to another very interesting representation of a positive definite matrix, which is that A can be written as a product of the matrix of orthogonal matrix of eigenvectors times a diagonal matrix which is made up of eigenvalues times again the transpose of the orthogonal matrix of the eigenvectors. So this in fact can be, if one knows Kerr's decomposition, which says that a symmetric matrix can be represented in this form, where this is the diagonal matrix of eigenvalues and Q is a matrix of the orthogonal matrix of eigenvectors. If we assume Kerr's decomposition, then we have already proved that lambda is greater than 0, and therefore this becomes a one-line proof from Kerr's decomposition. But since we have not done Kerr's decomposition, I will expand the theme a bit. It's essentially still the Kerr's decomposition only, but I'll expand the theme. So let me first show that if the two eigenvalues are not equal, then the corresponding eigenvectors have to be orthogonal, perpendicular to each other. So if say lambda, so let's take lambda I vi eigenvalue eigenvector pair. So I get a vi equal to lambda I vi, and for the another eigenvalue lambda j and the corresponding eigenvector vj, I get a vj equal to lambda j vj. And so if I look at vj transpose AVI from the first one, it becomes lambda I Vj transpose Vi. And if I multiply this second one by Vi transpose, then I get Vi transpose AVj is equal to lambda j Vi transpose Vj. But these being scalars, the transpose of them has to be same. So therefore, uh, this and this has to be same. But Vj transpose Vi and Vi transpose Vj are same. So and lambda I and lambda j we know are different. So these two can become equal only if Vj transpose Vi is 0, which is equivalent to saying that they are orthogonal. Now, what about the repeating eigenvalues? For example, if you look at the identity matrix, then the eigenvalue 1 repeats n times. So, what about that? How do we tackle the question of orthogonality there? So, to that end, let us say that there is an eigenvalue lambda and it repeats k times in the characteristic polynomial. Then corresponding eigenvectors are, uh, let these be the corresponding linearly independent eigenvectors of the repeated eigenvalue lambda, and they are repeating k times. So then first thing is that any linear combination of it is also an eigenvector. That is very clear. That follows from the fact that if I take a times some alpha j v lambda j, then this is same as alpha j times a v lambda times of j, which is same as lambda j, and now I can take this eigenvalue lambda out, and therefore it is lambda j times, sorry, alpha j times, this is alpha j times Vj, which is or V lambda of j, which is basically amounting to saying that this has become the eigenvector for lambda matrix. So therefore, we have come to this arrived to this simple conclusion that any linear combination of it is also an eigenvector. So what we can do is then apply Gram-Schmidt orthogonalization to this. Start with any basis of corresponding to this subspace of the eigenvectors for the eigenvalue lambda, and uh, apply apply QR decomposition or Gram-Schmidt orthogonalization to it, and extract a basis which is made up of orthogonal set of vectors. So if the basis is made up of, essentially what I am trying to say is, if you have a subspace, you have a basis for it which is essentially a orthogonal basis for it. So just look at the orthogonal basis for this subspace of the eigenvectors corresponding to lambda, eigenvalue lambda, and they will become the orthogonal eigenset of eigenvectors. Now put it all together. If the eigenvalues are different, then the eigenvectors are shown to be orthogonal, and if the eigenvalue repeats, then the corresponding basis of eigenvectors can be taken to be orthogonal basis, and this orthogonal basis is automatically perpendicular to the other eigenvectors corresponding to the other eigenvalues. So therefore, if I put all these n eigenvectors together, this and their length is unity and they are all perpendicular to each other, then this matrix of eigenvectors will become essentially AQI equal to lambda QI. Arrange it now, AQ1 Q2 to Qn to be equal to Q1 Q2 to Qn times lambda 1 lambda 2 to lambda n, and arrange it in such a way that it is in the non-ascending order. That is, lambda 1 is greater than or equal to lambda 2 is greater than or equal to lambda n for a proper ordering. And then you get AQ equal to Q times of lambda, the diagonal matrix, and A equal to Q lambda Q transpose, where this is Q transpose Q is again equal to identity being orthogonal. So if you look at it now with this set of ordering, I have actually directly arrived at the through Sker's decomposition and proper arrangement of the eigenvectors. I have directly arrived at singular value decomposition of the SPD matrix A, in which both the U and the V matrix are Q itself, the basis of the, it's in fact, so what we have said is that there is a orthogonal basis of eigenvectors for Rn itself. This is also the orthogonal basis for Rn, because we have n linearly independent orthogonal eigenvectors for A, and this becomes also your SVD of A. Now what I am going to do is, I am going to write this as first in this particular form, where lambda to the power half is the diagonal matrix which is square root of lambda 1 square root of lambda n, and square root of lambda n exists because each of the lambda i's in a SPD matrix are strictly greater than 0. And then I will now introduce Q transpose Q, which is an identity matrix in between here, and write it in this form, and then basically group this as one matrix and group this as another matrix and write it as product of two identical matrix, which I am going to notationally call it as A to the power half, because the eigenvalues are square root and the eigenvectors are the same. So this matrix is essentially called as the square root of the SPD matrix A. So we are saying now that SPD matrix has a square root of it, and when you square it, basically you get matrix A, and this square root matrix is also symmetric because this matrix is also symmetric. Now you take QR decomposition. So this matrix is also SPD because all of its eigenvalues are greater than 0, and it is non-singular because all its eigenvalues are greater than 0. So you take QR factorization, I'm just writing this as Q underscore bar times R of this matrix, and a to the power half is a to the power half into a to the power half transpose. So therefore this becomes QR times uh, Q, I'm sorry, not this way. I'm going to write this as a to the power half transpose a to the power half. So this is QR. I need to cancel this Q transpose Q equal to identity. I would need to use this property. So therefore, a to the power half a is equal to this is equal to this is equal to R transpose R. That is, and R is what? A upper triangular matrix, and I can assume without loss of generality that all of the diagonal values are greater than or equal to 0, and therefore this, in fact they are all greater than 0. I can assume that because if any diagonal becomes 0, then the corresponding there would be the matrix will no more be non-singular. So therefore, A can be written, a positive definite matrix can be written as R transpose R, which is known as the Cholesky decomposition of A. This can be computed in order n cube. We will look at the computational aspect in next class, but what we are saying is that it is a product of lower triangular matrix and SPD matrix is a product of lower triangular matrix and upper triangular matrix, such that the lower triangular matrix is just the transpose of the upper triangular matrix. So this is sufficient, this is both necessary and sufficient to prove that A is SPD. Because if A is SPD, this happens. And suppose you are able to get this decomposition, then it follows that, and R is non-singular matrix, then it follows that X transpose AX is nothing but X transpose R transpose RX, which is nothing but square of the length of this, and this, let's call this as vector y, then this is square of the length of y, which is anyway greater than or equal to 0. And but if R is non-singular, but if R is non-singular, that is all its diagonals are non-zero, in this particular case greater than 0, then what happens is, if x is not equal to 0, then y rx, which is y, will also not be equal to 0, and therefore what I will happen is this will become strictly greater than 0 for all x not equal to 0, making us clear that A is a SPD matrix. So if A is SPD matrix, R transpose R exists. If R transpose R exists such that R is non-singular, then automatically it follows that A is a positive definite matrix. So the way to check out a positive definiteness of a matrix is not through eigenvalue calculation. Eigenvalue calculation is an iterative process, but a Cholesky decomposition is just order NQ deterministic process. It's not it is not a iterative method. Therefore, otherwise, checking positive definiteness in optimization problems in the necessary and sufficiency condition would have become a big job. Fortunately, it doesn't become a big job because we can resort to Cholesky decomposition. I'll have more about it later on. Now let's me close with some other interesting uh, properties. These are just for theoretical interest. They don't make good way of calculating, checking positive definiteness of the positive definiteness of A, but still are interesting in their own rights, though not computationally elegant. For example, one interesting property that I want to mention is So I have this A11, A12 to A1N, A21, A22 to A2N, and ANN, I'm sorry, AN1, AN2 to ANN, and I look at this matrix and I extract any square submatrix like this. There are many possibles. You could just start with a one by one here, or a two by two block here, principal submatrix, or something in between, or take the first column, the second column, the seventh column, the eighth column, and first row, second row, seventh row, eighth row, whatever, many combinations are possible. So it becomes combinatorially, it blows out. That's why I'm saying that it's not a good way of computing it, calculation. But all such submatrices, the principal submatrices, will are also are also positive, symmetric, positive, definite. Follows from the fact, simple, that for others you just set these coordinates to 0, and whatever is this, I'll call this as x bar. Write this vector here like this: 0, x bar transpose 0 here. And if you if you expand it, what you are going to get is x. This is going to be same as x bar transpose x of this, but because this has to be greater than 0, this automatically becomes greater than 0. Why has this to be greater than 0? Because a matrix is positive definite, so any x not equal to 0 has to be this, but this is same as this, so this also becomes greater than 0 for all x bars, all possible non-zero x bars, which basically means that this submatrix also becomes greater than 0. So that's another very interesting characterization which you will see in many places. With this, I think I'm going to stop this lecture here, and computation of Cholesky decomposition and subsequently LU decomposition will be a topic for the next lecture. Thank you.